see all of you here again for our first Tuesday of the month seminar series. Today's speaker is our good friend Jim Smith. Jim is the William and Edna Macaleer Professor of Engineering and Applied Sciences and also a professor in Civil and Environmental Engineering. Jim, among many things, has served in a variety of different administrative roles at the campus, including department chair in Civil and Environmental Engineering from 2011 to 2017. His research, as you can see, focuses on extreme rainfall and extreme flooding, which is what he's going to talk to us about today. He's also done all sorts of fascinating work, including looking at impacts of urbanization, not only on the response of rainfall, but the impact of urbanization on rainfall patterns themselves, with lots of really interesting work around places like Beijing and how that affects rainfall patterns. Jim is a fellow of the American Geophysical Union, a fellow of the American Meteorological Society, AMS. Among other things, he was the Robert Horton Lecturer for AMS. And most recently, he has received a 2019 Hydrologic Sciences Medal from the AMS. I'll note this is one of the highest prizes given to anyone in the field of hydrology. And I'll just read the brief citation. It's for exceptional contributions to understanding physical and statistical aspects of flood hydrology, urban hydrometeorology, and hydroclimatology. Give you a sense of the sorts of things Jim works on. I'll also mention that he's a fantastic teacher. Among other things, has won the E-Council, the Engineering Council Teaching Award for his teaching of the undergraduate course in hydrology. So please join me in welcoming Jim Smith.
Thanks, Mike. So what I'd like to talk about is strange floods, and I'd like to begin by making the observation that arguably the strangest flood in U.S. history is the June 1903. Is the June 1903 flood in Heppner, Oregon. It's a terrible flood. More than 250 fatalities in less than an hour. It's strange in that the measured peak discharge is more than 100 times larger than the next largest flood peak. It's also strange in that it's produced by a hailstorm in a region where snowmelt is the dominant flood agent. Now, the hailstorm piece is also strange because kind of a standard view is that these are not the types of storms that we worry about in terms of extreme rainfall production. Bill Cotton and Rick Anthony's standard textbook make this point, as do a number of other summaries. So what I'm going to do today, the main thing I'd like to address is the nature of the upper tail of flood peaks, and what that means will become apparent as we move through some of the analyses. It will be motivated by problems in engineering design that are driven by assessing the largest possible floods that can occur in particular settings. Now, one piece, I'm going to use observations like those from the Balm Fork Stream Gauge in Heppner. Annual flood peak observations are the standard tool for looking at flood frequency analysis. Annual flood peaks, the annual maximum flood peak in a particular year. The metric that I'll use, or one of the metrics that I'll use for strangeness, is one that kind of came up in connection with the Heppner flood, and it's the ratio of the flood of record, not to the second largest, but I'll use the flood that occurs on average every 10 years, the 10-year flood. And that's roughly what I mean by the upper tail, the 10-year flood and beyond. So this ratio is going to be one of the principal tools for quantifying strangeness and looking at flood frequency. I will look at there are more than 8,000 stream gauging stations with long records that will be part of the analyses. Annual maximum flood peak, the basic idea is that you're making measurements over the entire year. There are a bunch of flood peaks and you're taking the largest. In the same way that when you take the average of a bunch of things, you get a normal distribution from the central limit theorem. There's a related result that says if you take the maxima of a bunch of loosely connected things, you get a different distribution, and it's called the generalized extreme value distribution. It'll be part of the framework for looking at floods in general, in particular characterizing strange floods. Now there are three parameters: a location mu, a scale sigma, and a shape chi. The form of the quantile function that gives you the t-year flood is given in terms of the return interval t and the three parameters. Now, the first piece on the nature of extreme floods, there are these wildly different worlds. One in which the shape parameter is negative, and there is an upper bound, and it's the location minus the scale divided by the shape. And the other where it's positive, and large positive is not just unbounded, but it's strange. And strange in the sense that even if you have long records, you may not see things that really are kind of going to control the largest possible thing that can occur. So this is one way of thinking about strange. Looking at stream gauging observations across the United States, and thinking about it in this GEV framework, a couple of points I'd make. One is location and scale are really size. And size here is drainage area. These are just results for the Potomac River Basin. The same kinds of results show up across the United States. So location and scale or size, location and scale are almost one-to-one relationships. Shape, on the other hand, isn't related to size, and it's not related to anything about the drainage basin that we can sort out. And it is going to really characterize many aspects of the nature of the upper tail of flood peaks. Now, the main theoretical result is that with some reasonable assumptions, if you look at this quantity, the upper tail ratio, it only depends on the number of years of record and the shape parameter. The shape for the upper tail ratio is the same, but the location and the scale, they're just functions of the number of years of record and the shape parameter. So we've got all of this size stuff out of the way. And we've got something that really just deals with the nature of the upper tail. The main prediction that comes from this is that the upper tail ratio shouldn't depend on size. It shouldn't depend on drainage basin area. And that's remarkably validated by looking at these 8,000 stream gauging stations. So this is just looking at deciles of basin area from the lowest tenth on the left, the largest tenth on the right, looking at distributions through box plots, the median in the middle, interquartile range, and then measures of low and high extremes. The distribution is just largely unchanged with area. And so it points to this way of looking at extremes through the shape of the GEV distribution being a reasonable way of doing things. Now, the bounded, upper bounded piece is a big deal, and design and approaches for extreme floods split in the 1920s. The bounded assumption is really what drives design up to this day, and it's really looking at how bad floods can be based on how large rainfall can be. And so that's set in place in the 1920s. It's largely set in place by Robert Horton, one of the preeminent scientists, hydrologists of the 20th century, and he was convinced that floods are bounded, and they're bounded because rainfall is bounded, and that is the way that you should think about extreme floods. So all of the tools that are used for designing high hazard structures now sort of revolve around this assumption. Probable maximum precipitation is the rubric that I'll come back to that's principally used for these kinds of design problems. Now, one piece of the observations, and here I'm showing the estimated scale parameter for all the flood peak records in the US, GEV scale and this upper tail ratio, and essentially they have similar information content. So extreme upper tail ratios are tied to extremes in the GEV shape parameter. More than 80% are positive, and so at best, Horton's assumption isn't validated by observations. Observations say that flood peaks are unbounded and strange in this connection between upper tail ratio and the shape parameter. So I'll use, one of the things I'll use is the upper tail ratio as a way of looking at the geography of the really big floods in the United States. One look at the geography is looking at the stream gauging stations that have upper tail ratios between 5 and 10 in blue, 10 and 20 in green, and larger than 20 in red. So Heppner in the upper left portion in the northwestern U.S., an upper tail ratio of 200. It's the largest in the stream gauging record, so 200 times larger than the 10-year flood for the June 1903 peak. The main conclusion from these analyses is that the largest upper tail ratios, the strangest floods, are west of the Mississippi River, and oddly, they're principally associated with hailstorms. Now, hailstorms, I use that as a measure of convective intensity, and there, thunderstorms sit in the middle. Hailstorms and the most extreme version, supercell thunderstorms, are on the most extreme end. And then there are convective storms that don't produce thunder and lightning. So hailstorms are a measure of convective intensity, and like the reports for the 1903 storm, we often have evidence that says that these are hailstorms. And so more than half of the large upper tail ratios in the western U.S. are associated with hailstorms, contrary to what Cotton and Anthus would assume about flood peaks. Now, a couple of other observations about the geography of large floods. One is that large floods really don't care about forest cover. It's kind of, in terms of the nature of flood peaks, one of the ways we think about floods is that, forests prevent floods. In fact, that was a rubric for the conservation movement in the early 20th century, and it's still part of the discussion that's used both in the U.S. and abroad. And forests have very little impact on floods, particularly the largest floods. This was settled science within the Forest Service by the 1960s, and it's certainly borne out by these analyses. So in the nature of flood peaks, forests really have little impact. There's a strange one, Bob Jarrett's 7,500-foot hypothesis, based on just observations, geomorphological observations of floods in the Front Range of the Rockies. He concluded that you can't have extreme floods above 7,500 feet. It's about 2,300 meters. And if you look across the entire U.S., there is indeed this big drop in flood peaks for the set of stations that are above 7,500 meters. So Jarrett's hypothesis is, in fact, it's a piece of the geography of strange floods. Bill Cotton weighs in on this, and he argues that hail really leads to the presence of hail above 7,500 feet is what leads to diminished rainfall from these storms. It's a big deal because the Bureau of Reclamation has a lot of dams with drainage areas above 7,500 feet, and the concern is that the designs for those dams didn't deal with the flood hazards that they would face. And so the hail argument by Cotton supports and provides some grounding for this. Now, one problem when you're looking at a design standard that is an upper bound that it can't happen is that when it does happen, it's problematic. Castilla Creek is in the Sangre de Cristo Mountains. The entire basin is above 9,000 feet, and it has a much, much larger flood peak than in other settings, one of the greater than 20 upper tail ratios. And so it's a hailstorm during the North American monsoon season. And so it is a counterexample. How does this happen? Becomes one of the really central questions in looking at the climatology of these peaks. Now, the same kind of question comes up. Heppner's sitting up here, and is it just kind of a sort of a strange occurrence? The results for large shape parameters, say weird stuff can happen, and can we just simply write it off to that? Or is there sort of a larger setting in which we can place floods like the Castilla Creek flood and the Heppner flood? And it turns out it's the latter. Heppner is not the largest flood peak in the region. In fact, there are two much larger flood peaks, all of them located along the north slope of the Blue Mountains in the deserts of eastern Oregon. Lane Canyon and Myers Canyon define the envelope curve of flood peaks, the largest flood peaks in the US and the world. So these are observations of flood peaks versus drainage area. There are miscellaneous flood peaks, meaning that there is never a systematic stream gauging station installed, but the US Geological Survey made discharge measurements for these sites. So Lane Canyon and Myers Canyon, they're two of the biggest in the US. Now, EC, I'll come back to that, Eldorado Canyon in the southwestern US. The three are, in some respects, the biggest flood peaks for which there are measurements in the United States, the most extreme flood peaks in the United States. So a piece of the story here is that this flood, in which the flood peak magnitude of the Heppner flood is 200 times larger than the 10-year flood. It's not in isolation. It's part of a larger collection. There's a climatology associated with these types of storms that's important for assessing extremes. And so what I'd like to do is look a bit in detail at this particular setting. So we're in the Colorado Plateau of eastern Oregon and Washington, and we want to understand why really big floods happen in this setting. Now, so this is a geographic representation. The states of Washington and Oregon, the Columbia River is the boundary, the Columbia Plateau to the north of the Blue Mountains. Now, 1, 2, and 3 are the locations of the Heppner, Lane Canyon, and Myers Canyon flood peak measurements. So they're on the north slope of the Blue Mountains. The background map is a representation of thunderstorm frequency. And so the big picture here is thunderstorms form over the high terrain of the Blue Mountains, and then they're going to evolve, and how they evolve plays a big role in these flood peaks. So this is the setting. We've looked at each of these three floods. In particular, we've looked at the storms that produce these three floods, and we've done it using a regional climate model, the weather research and forecasting model. We use 20th century reanalysis fields for initial conditions and boundary conditions, and we've reconstructed these three storm events. So the upper figure is just rainfall. There's a 70 millimeter max. It's not located over Heppner, but it's on the north slope of the Blue Mountains. What we know about rainfall on June 14, 1903 is in broad agreement with this feature. Now, the point I'd like to focus on is they're just characteristic features for these three storms. They all have a trough off the coast, so a trough in an extended region of low pressure. It's unusual in June and July. There's kind of a semi-permanent low that sits off the coast in winter, but by summer it's usually moved well to the north, or it doesn't exist. But this happens. More unusual are the precipitable water values. This for Heppner is the precipitable water field. 35 millimeters of precipitable water turns out to be right at the upper bound for this particular region. So the extremes in precipitable water, it's a multi-day period. It's hard getting water vapor into the Colorado Plateau. The troughs, they were reasonably frequent. These aren't associated with the water as high convective potential. Storms form over the Blue Mountains. Now the trough, the piece there that's important, is trough sitting to the west. The winds over Oregon are blowing south to north, and so the storms are all going south to north. And those are the kind of the principal elements of the Heppner storm, and they're analogous analogous for Myers Canyon, and they're analogous for Lane Canyon. So it's not simply just a one-off in which we've got a single extreme event that's coming from nowhere. There's a systematic element to the geography and the environment of these storms. Now, it doesn't seem like that big a deal, but the south to north motion actually is a reasonably important feature. Looking at how you build a flood peak on the north slope, this is the setting for the Heppner flood. So Willow Creek, Balm Creek flows into Willow Creek, and Heppner is here. We know a lot about the June 1903 storm from the USGS reports that were carried out. We know the storm formed on the high elevations of the Blue Mountain. We know it moved south to north down the basin. It was about about as wide as the drainage basin, and it rained for about 30 minutes at any particular location. So there's a lot of information about the storm, and one of the things that we can do there is we can reconstruct the flooding, and this is one way of reconstructing the flooding, and it's simply taking a circle with a constant rain rate, having it move at a constant velocity through Balm Fork. And we move the rain rate up and down. Now, we move it two ways. We move it down the basin, which is what happened, and we move it up the basin. Down the basin gives you twice the flood peak of moving it up the basin. So the fact that we have south to north moving storms, we have storms forming on the Blue Mountains, there is a very pronounced geographic structure to both the storms and the way they translate into floods in this particular setting. So that's one piece of it. The rain rates are really large, so we need about 150 millimeters per hour. So it's 150 millimeters per hour going up or going down. Same amount, it's 30 minutes, so we're getting about 75 millimeters. That's about the right amount of rain based on USGS analyses. But 150 millimeters per hour for 30 minutes is extraordinarily rare in Oregon. So we know an awful lot about these storms, but there's still some pretty significant mysteries. And so one of the things we wanted to do is we wanted to look for modern analogs to the storm. And modern, I principally mean the radar era, so that begins in 1993. Has there been anything like the Myers Canyon, Lane Canyon, Heppner storms in the modern observing record? I guess the short answer is no, but there's one that's close. And the closest was a storm in July of 2012. And it has all the environmental features. It's got the trough off the coast. It's got near record precipitable water, the 35 millimeters. It's got the high convective potential. And this storm, which is shown in reflectivity measurements from radar on the left, it's moving just west of Balm Fork, and it produces a minor flash flood in the area. It's a big hailstorm. It's producing large hail like the Heppner storm, but it just doesn't quite do the trick. Now, the measurements here of a weird quantity. It's a polarimetric radar, and it's called specific differential phase shift. The basic notion is it gives us clues in a hailstorm what's happening with rainfall. And a simple message is there's a very, very brief time in a small portion of the storm in which there are extreme rain rates, not Heppner-like, but extreme rain rates. And so one piece that's kind of missing is this piece that's tied to extreme rainfall. So we know the climate piece in this particular part of the world, we've got a good grasp on it. But the rainfall rate piece is problematic. So what I'm going to do now is I'm going to switch to another arid, semi-arid region, the Colorado Plateau, Colorado River, Grand Canyon, Lake Powell. And I'm really going to focus on a storm Short Creek is 50 square kilometers. There's a 5 square kilometer sub-watershed Maxwell Canyon. That's really what I'm going to focus on is Maxwell Canyon. I'll be comparing floods, though, to a number of these Colorado River drainage basins, the Dirty Devil, Escalante, Paria, Kanab, Virgin, Fort Pierce Wash watersheds. So these are the north to south draining rivers into the Colorado River. So this is the setting. And the story is really the precipitation story. And oddly, the story was known back in the 19th century. G.K. Gilbert gave a wonderful characterization of what he refers to as the paroxysmal precipitation of the desert. The quintessential example is a storm that occurred on September 14th, 2015. So these are radar observations. This is the track of the storm that's based on the radar observations. Lightning, it's a year's worth of lightning over Short Creek and down into the East Fork of the Virgin River, and really sort of all concentrated around Maxwell Canyon. So this is one of the largest flood peaks in the U.S., and how this storm behaves is something we want to think about. Now, largest flood peaks, Maxwell Canyon sits here. This is looking at the Colorado Plateau area versus flood peaks, 5 square kilometers. Now, the green points here, these are flood peaks at systematic stream gauging stations, flood of record. The X's are miscellaneous flood peaks, and the blue peaks are paleo flood peaks from Vic Baker's group at the University of Arizona. So these go back more than 1,000 years. Now, Eldorado Canyon, also September 14th, 1974 in this case, it was the one that was sitting on the US envelope curve, like the Myers, like the Maxwell Canyon flood. It's an extreme hailstorm. It has Heppner-like reports of hail associated with the storm. And at 50 square kilometers, it's larger than any of the flood peaks up to 10,000 square kilometers. So it is the paroxysmal precipitation of the desert associated with the most extreme form of convection that produces record flood peaks. Now, Maxwell Canyon, it is, so this is, for its size, much larger than anything around it. It also turns out that the storm moves up in the East Fork of the Virgin River. This is the tracks of the storm. The Virgin River is almost 1,000 square kilometers. It's less than 20 minutes, and it's the flood of record in the East Fork of the Virgin River. So this scale, it's not area that matters, it's size of storms, and it's the intensity of rain rates from these storms that drives the magnitudes of flood peaks. So 1,000 square kilometers doesn't matter. What matters is that we have extreme rain rates close to the basin outlet. Now, just a few quick comments about the climatology of North American monsoon thunderstorms. This is looking at the Colorado Plateau. It's essentially thunderstorm frequency. It's from the cloud-to-cloud lightning flash density. So we've got about a factor of 5 difference between the high plateau regions and the desert, the low elevation Glen Canyon, Lake Mead, the Escalante Desert. So we have a very pronounced spatial gradient in the occurrence and motion of storms. The North American monsoon, it begins rapidly in July. The peak is July and August. It extends into September when we have these really big events, but it is a much lower frequency of storms. Now, so this is one look at the climatology. Another look at the climatology is just based on looking at all the storms that produce flash floods in the Colorado Plateau from 1998 to 2015. With radar observations, there are 360 days, so we tracked all those storms. We looked at motion, intensity in a various way, and size. Now, I'll just point out a couple of features that are important. Almost everything moves from the southwest. It makes perfect sense. The monsoon moisture surge is bringing water from the Pacific through the Gulf of California. So the flow that's bringing moisture is also going to largely be the winds that steer these particular storms. It becomes more pronounced later in the season. There are fewer of these. They are all associated with troughs that are moving in from the Pacific. So we add that to the mix. The 2015 storm, it was moving southwest to northeast, but it was 50 to 60 kilometers per hour, way on the upper end of storm speed. It was at the very high end of convective intensity, and it was 50 to 60 square kilometers. So this is just a spatial detail. The southwest to northeast motion dominates, but terrain modulates the way thunderstorms behave in this region. And so the same kinds of stories as we saw with storm motion and terrain in the Blue Mountains play out throughout the Colorado Plateau. Now, I want to take a short digression. And so these are hailstorms. They produce unprecedented flood peaks and presumably unprecedented rainfall rates for short periods of time. How do you do that? So the larger question that we're wrestling with is how hard can it rain? And one way of thinking about how hard it can rain is how hard it has rained. These are hailstorms back in the central Appalachians. The world record, or the U.S. record, it's no longer the world record, 1875 millimeters per hour in Unionville, Maryland. Smethport, 1,000 millimeters per hour at 10 minutes. The D'Hanis storm in 1935, 200 millimeters per hour over 2 hours. The D'Hanis storm, there's a tornado associated with this storm, so it is clearly a supercell in addition to producing large hail. These both produce tremendous amounts of hail. So it is the most intense forms of convection that are the types of events that we're worried about and think about. One conjecture is that it's really the end member that is the most that's capable of producing the largest rain rates, and that's supercell thunderstorms. Model organism, the reason for thinking in those terms is they're clearly important. They produce extreme rain rates and big floods. They've been studied to hell too, because these are the storms that produce tornadoes. The characteristic structure, tremendous inflow of moisture to the storm, spiraling updrafts in which hail is produced, and then downdrafts, forward flank downdraft. The rear flank downdraft is where the tornado is located if it occurs. So that's where the attention is focused. The forward flank downdraft is where we get extreme rain rates. It's been examined quite a bit because it affects the way the forward flank downdraft behaves and the way tornadoes form. So we know a fair amount about this type of storm simply because it's been examined as an agent of tornadogenesis. The biggest tornado in U.S. history was the El Reno tornado in May of 2013. At one point, the tornado was 4 kilometers wide. Now, the tornado resulted in 8 fatalities, and so that's terrible. Reflectivity, here's the hook echo, the rear flank downdraft, the forward flank downdraft, and this tremendous inflow into the storm that sort of drives the way the storm works. Now, polarimetric measurements, they tell us about this storm, and one of the things they tell us is what happened here. There were 8 tornado fatalities. There were a lot more flash flood fatalities. We don't know how hard it rained. It rained extremely hard in this forward flank downdraft. We know a lot about the mechanisms that take condensate that forms in the updraft and place it in the forward flank downdraft. That ultimately is the way we need to proceed to understanding how hard it rains, or how it rains hard. Now, back to the Colorado Plateau in the 2015 storm. It's moving extremely rapidly, so it produces 13 fatalities downstream of Maxwell Canyon, sort of fades out. Then it produces 7 fatalities in Zion National Park, and the flood of record in the East Fork of the Virgin River. So the paroxysmal precipitation of the desert is precisely what this is. The radar observations provide us with useful ways of looking at how it rained hard in this particular day. So this is a 20-minute time period. We have a hail core sitting in the northwest portion of the storm. We have tremendous inflow to the storm. The velocity data tell us that. And then we have these brief periods that are 15 to 20 minutes in duration, a smaller portion in which the precipitation that's going to fall over Maxwell Canyon organizes. So it organizes tremendous rain rates over Maxwell Canyon, and this sort of dies out for about 20 minutes. Now, from the procedures developed by the community looking at supercells from polarimetric radar observations, oddly, the source of the water at the ground is principally melting hail and liquid water that's shed from hails. It seems odd that that's going to produce tremendous flood peaks, but that's what this evidence suggests. It also suggests that it's a downdraft, and one part of extreme rain rates is getting really, really strong downdrafts, and it points to negative buoyancy, evaporation of rain, melting of hail, and precipitation drag as being really important features in determining the magnitude of the rain rates. So that's part of the story. It fires up over Maxwell Canyon. It sort of fires down, but then it fires back up when it approaches Keyhole Canyon and the East Fork of the Virgin River. And so the process repeats itself in what Gilbert aptly described the paroxysmal precipitation of the desert. So these are the key elements that we need to understand and looking at events like the Eldorado Canyon flood and assessing the potential magnitudes of extreme floods in a variety of different settings. So I guess what is the nature of the upper tail of flood peaks? Just several observations. It's strange in ways that that we can assess through tools like upper tail ratio and the GeV scale parameter, and it points to kind of specific aspects of strangeness. It's strange in ways that where our conventional wisdom doesn't really serve us well in assessing what is responsible and what can produce the largest flood. So a hailstorm in a region dominated by snowmelt is kind of the quintessential example. They play out throughout the United States. But the flip side of it is that we understand enough about the geography and environment of these storms, like the ones that we were looking at in the Colorado Plateau and the Columbia Plateau, some of the most extreme settings in the U.S., that they are not simply anomalies, but we can look at the climate. The big hole is we don't know how hard it can rain, and we really don't know how it rains hard, and that's really the key aspect of strange floods. So thank you, and I'd be happy to answer any questions.
So, for example, how the convection actually affects the area around the storm itself, but does it also affect the area from which moist air can be drawn in? Or is that so local that depends much more on the
Yeah, one of the things I didn't focus on is the reason convective intensity is important is that vertical motion can give us convergence, and it can expand the inflow to the storm. And so the basic argument for convective intensity being important is that you really converge more water vapor into the storm, and you expand that area.
Can you estimate that area?
Well, so it varies with settings. So the storms in 2015, there's a tremendous monsoon surge, and so we can characterize that. And then from the Doppler velocity observations, we see how it's amplified into the storm. But there's this larger setting that is doing a lot of the work in providing the water vapor.
Thank you very much. That was great. There's been some recent literature in the discussion about temperature extremes and mortality suggesting that if you look at the full distribution of temperatures, a lot of the mortality associated with temperature comes from only slightly abnormal temperatures,
Yeah.
so like slightly too warm,
Yeah.
slightly too cold, and
Yeah.
previously we weren't really accounting for that. And I'm curious, if you have, whether it's an anecdotal sense or like actual data suggesting whether mortality associated with precipitation is really mostly occurring during these extreme events, or even if you have a bit of rain that
Yeah.
increases mortality as well.
Yeah, good question. Mortality in flash floods is people driving cars through flooded waterways. Then there are some in the tropical cyclone world. Hurricane Camille in 1969, the east slope of the Blue Ridge. It's nighttime, and it's producing a tremendous flood in an area with a lot of people in the valley bottom. So with flood fatalities, there's this combination of, especially with tropical cyclones, where people are located. With thunderstorms, it's mainly it is mainly tied to people driving when they shouldn't be driving. Yes, thanks.
Thank you, that was great. A question with the two Colorado floods, or the Colorado Plateau floods,
Yeah.
both being in September. I know it was driven by monsoon connection. Was there a tropical connection too?
No. It's a good question, and so the literature looking at probable maximum precipitation, it harps on tropical cyclones contributing water vapor to some of the really large storms. And I'm kind of on the negative side of that actually being a big part. In some of the places where it's been identified, I think the storms themselves did a fine job without the cyclones.
It's very interesting that it's due to hails that the flood is so intense. Is it probably also because it protects it from evaporation as it comes down? Because it's the fact that it melts very slowly.
What is taking place in these downdrafts? There's not much evaporation taking place. These are the people that have been caught in these events. They refer to feeling like they're drowning, and reaching shelter is breaking water. So it is very difficult to imagine what these downdrafts are like. But evaporation's not going to be a really big player.
It would still not be a problem. It would not evaporate like that.
Yeah. Oh, so there will be evaporation will be taking place. The mass of water is just so large, and it's so close to saturation that it's not a big deal.
I was just wondering, because of the tornado, Sunday wasn't exactly
Yes. Yeah.
If you had any thoughts about how that might fit into, was there very much water with that?
Yeah, so I advertised the Mississippi River flood. And for those of you coming to hear Mississippi River flood, I apologize. But the Mississippi River flood story is the storms like the ones that produce these tornadoes. The 1927 flood is a series of powerful extratropical storm systems, but there's this coupling of the most extreme forms of convection with tornadoes and heavy rainfall. That's a big part of the Mississippi River story. It's a story in 1927 and in 2011 where we came that close to repeating 1927. Yeah, so that's an important point.
I want to ask you something about the flood in Thailand, because you have a slide show that the forest cover has little impact on the extreme flood. Yeah,
Yes.
But in Thailand, there are a lot of flood events, and always they complain for the upstream deforestation.
Yeah.
Do you have any something?
Yeah, so I'll give the simple argument here that from the Forest Service, and that is looking at extreme or looking at the impacts of forests. One of the things in the 50s and the 60s they worked on is, how much can it be? And sort of the range they came up, or the characteristic value, is about 1.5 inches of storage. And so when we look at in the eastern U.S., the forested eastern U.S., Camille with 30 inches, Smethport with 30 inches, hurricanes producing more than 20 inches. The forest impact at its largest is within the noise and the precipitation. That's largely what the previous Forest Service studies have shown. So if you've got settings where the storage capacity gets larger than that, and the amounts of rainfall that produce the bigger floods moves down, then forests may have impacts. I think it's certainly the case that the forest prevents floods mantra has not captured what the forest science community thought about floods for much of the time. Yes?
I have a question about if you had all the meteorologically relevant data available that you have from satellites and so on, and you had all the stream gauges you wanted, is there really a strong predictive connection between what you measure up there from what you see on the ground? Is that scientifically explained?
So from there's
So that would
there.
be big variable, the soil, the geology, the forest cover.
Yeah, certainly the satellite remote sensing observations provide useful information on extreme rainfall around the globe. In the United States, less so. The radar network provides much more detailed information about rainfall at the ground. So the modern observing capabilities give us the capability of doing reasonable jobs with the rainfall.
Use one to predict the other.
Produce the flooding from the rainfall? Yes, that's sort of day in, day out. The National Weather Service and forecasting agencies around the world, they do that. And there are sources of error, but flood forecasting is an advanced tool.
I have a question. Thank you for the interesting talk. So according to the data you have shown that the most extreme flood seems to be happened in early 20th century, which makes sense because there were less dams.
There were less
dams.
Yeah.
So, but there were also like the figure you showed, slide you showed that the most extreme precipitation events were also before 1950s. So is there any explanation for why that is the case, or is that contradictory to like the current understanding that with global warming you see more extreme flooding?
Yeah, there's really no direct evidence for higher rainfall in many settings in the U.S. in the early part of the 20th century. A piece of that story in the Colorado Plateau is what's called the Arroyo Problem, and it's tied to observations that beginning sometime in the late 1860s, the rivers in the Southwest, they began trenching and widening dramatically, and that happened until the 1920s or so. By the 1950s, it had been reversed. And the sort of prevailing theory on why that happens is that it's principally due to sort of decadal scale variability in extreme rainfall. And so this period from the 1870s to the early 20th century in the southwestern U.S. had higher rainfall. The Colorado Compact was signed in 1922, and it was the wettest. So that's the way water is allocated in the Colorado River. It was the wettest 10 years in the historical record, which is 120 years, and paleo flood data suggests the wettest in 500 years. So there are these, certainly these variations in precipitation.
Question, which what's the characteristic of the storm that gave the largest flood around Princeton and Stoneybrook or the Millstone area?
The largest floods in Stoneybrook are tropical cyclones, so Irene in 2011, Floyd in 1999, and then there have been a few winter-spring events that are kind of comparable in magnitude, and they are tied to not as much rainfall, but completely saturated conditions.
Seeing no questions, let's thank you again.